In Chapter 3, we'll start off with a brief discussion of chemical equations and the qualitative side of those, some classification of reactions, and then we'll get into the quantitative part of chemistry, starting with formula weights, talk a little bit about Avogadro's number, empirical formula, stoichiometry, and limiting reactants. First of all, reactions on the particle level. Here we see a Bunsen burner in which we have methane gas being brought in through the tube at the bottom, reacting with oxygen, which is going in through the small holes at the bottom of the tube, reacting together to form carbon dioxide and water. So on the particle level, we have the methane molecules and the oxygen molecules forming carbon dioxide molecules and water molecules. And the symbols that are used here, the shapes, should be somewhat familiar to you. And then we have the symbolic representations underneath, the CH4 for the methane, O2 for the oxygen, and then CO2 and H2O for the carbon dioxide and water, respectively. Balancing of chemical equations would involve making sure that we have the same number of atoms of each element on both sides. We want to make sure that we aren't in violation of the law of conservation of mass. It says atoms cannot be created or destroyed. So you see in the reaction that we were just dealing with, if we take one molecule of methane apart, we get one carbon atom, 4 hydrogen atoms. We would then need to take apart 2 molecules of oxygen to get 4 atoms of oxygen, and then those would be used to put together a molecule of carbon dioxide and 2 molecules of water. Now, the way we learn to balance equations from just the symbols without having to deal with the particles is to look at the equation and write down a 1 for the most complicated part. So if we look at the top equation here, I'm going to put a 1 in front of the first reactant. That gives me 3 zincs on the left, and in order to get 3 zincs on the right, I would put a 3 in front of the zinc hydroxide. I have 2 antimonies on the left, so I'm going to go over to the last product and put a 2 in front of the last product, so I have 2 antimonies on the right. Notice that I've left hydrogen and oxygen for last. They usually are the hardest ones to balance. Since oxygen is only in 2 places, I'm going to go ahead and balance that. So I'm going to use the product zinc hydroxide to identify that there are 6 oxygens on the product side. To get 6 on the reactant side, I would put a 6 in front of the water. And so this would be our balanced equation. In the second equation, the first substance looks like it would be the most complex, so we would put a 1 in front of there. That gives us 1 boron. To get 1 boron, we would swing over to the product side and put a 1 in front of the BP. We have 3 chlorines, so I would swing across to the right, and to get 3 chlorines on the product side, I would put a 3 in front of the HCl. Now, when I go to balance the phosphorus, I'm going to realize here that I have kind of an odd-even problem or a deficiency problem. Notice that on the product side, I have 1 phosphorus, and over on the reactant side, I have to have at least 4. So what this is going to involve then is, ordinarily for an odd-even problem, we would double. In this case, we can see that we're going to have to multiply everything by 4. So if I multiply this one by 4, I have to multiply each of the other coefficients that I've put in place by 4 as well, so that their balancing will not get thrown off. Then I can go back and try again. So now I have 4 phosphorus on the right. I can get 4 on the left by putting a 1 in front of the P4. And again, I've left the hydrogen for last. I have 6 hydrogens on the right. And to get 6 on the left, I would put I have 12 hydrogens on the right, the product side. To get 12 on the reactant side, I would put a 6 in front of the H2. And so here is our method for balancing equations. So we will need to practice these. Next, we're going to go over the basic types of chemical reactions, or the patterns of reactions. Eventually, we'll get to the point where, similar to last year in honors chemistry, we'll be asked to predict the products of reactions. But for right now, we'll just work on identifying the types of reactions that are involved. So a combination reaction or a synthesis reaction involves two substances combining together to make a product. Decomposition would be just the opposite. We would have one substance that would then break apart into two or more separate substances. Combustion, usually we're dealing with combustion of hydrocarbons, compounds that contain both carbon and hydrogen. Of course, sometimes they also can contain oxygen, but these are going to react with oxygen gas to produce water and carbon dioxide gas. Okay, so this would be a combustion reaction. Next, we have single replacement reactions, where we'd have a single element that would react with a compound, and we actually had the possibility of replacing either the first element, or usually the metal, to form a different compound, thus replacing the metal that was originally with the nonmetal. Or we can replace, if we start with if A is a nonmetal, it can replace the nonmetal part, producing, again, a new compound, but in this case it's the nonmetal that's been replaced. And then the other main category of reactions that we have is a double replacement. In which case the cation and anion combinations switch. And usually one of those products is either water, a gas, or a solid. Now the final two, single replacement and double replacement, we're going to be going over those in more detail in Chapter 4. So we'll take a quick look at combination, decomposition, and combustion. So on your own, just take a moment to classify each of the reactions here that are in front of you and bring your answers to those to class. So here's one of the reactions that we had in the page prior, the reaction of magnesium with oxygen. And you can see here that the magnesium ribbon actually combusts. There's combustion going on here to form magnesium oxide. So it's a combustion as well as a synthesis reaction. So combustions don't necessarily have to produce carbon dioxide and water. The other thing about that equation, I'm going to rewrite it up here, is it can also be classified as an oxidation-reduction reaction. Most synthesis, decomposition, combustion, and single replacement reactions can be classified as oxidation-reduction reactions. Oxidation is the loss of electrons, and reduction involves the gain of electrons. You can't have one without the other. If one thing's losing electrons, it has to be gained by something else. If something's gaining electrons, they must be lost by something else. So if we go up to the original equation up at the top here, and we look at that, any neutral element is going to have an oxidation number of 0. So that would be both the magnesium and the oxygen. And then over on the right, we're going to give oxygen an oxidation number of -2. And for this to be balanced, the magnesium would have to have an oxidation number of 2+. Obviously, for the magnesium to go from a 0 to a 2+, it must have lost 2 electrons. Oxygen, to go from a 0 to a 2-, each oxygen atom must have gained 2 electrons. If you took the balancing into account, the loss and gain of electrons would also be equal. The saying that we used for this before was, to help us remember that oxidation reduction, is the lion goes grr. Leo lion goes grr. Lose electrons, oxidation. Gain electrons, reduction. Now, determining the oxidation numbers for the elements, there's some rules in your book. We'll go over those in class. It's one of the activities that we'll do. The website at the bottom here will give you some practice also at determining oxidation numbers for different elements. So if you go to that site, it's a mahjong, if you've ever done that. So it's kind of an interesting activity.